Today we're going to talk about the relationship between position, velocity, and acceleration. So here's a time versus position graph, right? And as time goes along, let's say whatever this object is going in there. We'll just say it's a bird. Okay, so he's at level 0, the position is 0, and he's just standing on the ground. And as time moves, he's going higher in the air. And then he starts to come down and, oh, he sees a fish in the water. So now he's going to go below sea level, right, and going down to the water, get his fish, and then come back up, right? So this is the relation, this is a graph of time versus position. Well, this is important because what is the relationship? I'm just going to move down here. We know that slope is rise over run. If we take that same idea about slope, and we come over here, and let me put this back over here. Notice our slope at 0. Okay, the bird is going up. And as we move forward, let me grab that little dot. As we go forward, it's kind of hard to see on this video, but you know the slope is getting a little bit less steep. So the bird is going up in the air at a pretty decent velocity or speed. But as he starts to decide to turn around, see his speed or his velocity changes direction. At a moment in time that you can't even see, he's like at 0 speed, 0 velocity. And he starts very slowly, okay, accelerating as he goes down. So this is a small slope, okay, a little bit of slope, even though it's in the negative direction, but now it's getting steeper and steeper and steeper. At this point right here, as he's passing the time 6, the slope doesn't change. See how it kind of stays the same? And then as he gets down here, catches the fish to go back up, he slows down a little bit to grab that fish, and then whoop, he's going to go back up. So if we did this in time, he's going to be going faster here, but as he changes direction, he slows down, and then he's going to go faster here as he spins around, right? So why is that important? Because watch, let's look at concavity. You see the blue part right here represents the concavity. This is concave down, and this is concave up. Well, notice the bird, as his as his velocity is he's getting faster. As his velocity is slowing down, his acceleration is also slowing down, right? So acceleration, he's going slower as he makes this curve, and concave is down. And as the bird continues to go forward, okay, the bird's starting to speed up. I can't grab the little dot. Starting to speed up right here. Let me grab the dot. It worked perfectly before. Okay, as we're going through. Okay, then here's the bird. He's like whoosh, and he gets the fish and comes back out. This is concave up. Okay, so let me explain why this works. Let's go to a piece of paper so I can explain what I'm trying to say. Is the relationship between position in time, velocity in time, and acceleration in time. These three are related, and they are hard to see. Okay, position in time, velocity in time, acceleration in time. They are all related by taking the derivatives. Now, position is usually represented by S, and then V for velocity, A for acceleration. Position sometimes is also represented just with X, like where it is along the X-axis. Okay, so if I take the derivative of position, I get velocity. And if I take the derivative of velocity, I get acceleration. Okay, so going this way, you take the derivative. Okay, this is the magical trick. Zvala, S-V-A, zvala. You go this way and you take the derivative. But if I have acceleration and I take the integral of acceleration, I'll get velocity. And if I take the integral of velocity, I'll get position. So this is how things are related. And then, if I take the second derivative, right? If I take the first derivative, I get velocity. Take the second derivative, you get acceleration. Take the integral of acceleration and get velocity. Well, if I take the integral of that again, I will get the position. So you're going to go this way by taking the integral. Okay, let's look at a few examples that I have. I'll probably just keep using this pen. Okay, I'm going to start with example 2. It says a particle moves along the x-axis so that its position any time greater or equal to 0 is given by x to the third minus 6x squared plus 4, or plus 12x plus 4. Determine the v of t. Well, this is x in terms of t. This equation represents my position, whatever that equation looks like. To get to my velocity, x prime of t equals velocity of t, and so that's going to equal 3x squared minus 12x plus 12. That equation represents the derivative of that. Now it says determine the intervals in which the particle is moving right. Well, if you are on the x-axis, right, moving right is going towards the positive direction. So we basically just need to find the critical points because we took the first derivative. I want to know at where it's moving. So I'm going to go ahead and I'm going to see what's happening with my velocity. When is my speed going in the positive direction? Because my speed in the positive direction, okay, my speed in the positive direction will be to the right, and in my negative direction I would go left, because everything's kind of based on the x-axis. So we're going to take 3x squared. Let me come down here where there's a little bit of space. I'm going to take 3x squared minus 12x plus 12. That's my first derivative, and I'm going to set it equal to 0. So let's factor this. First I'm going to pull out a 3 and get x squared minus 4x plus 4. And I can see that I can factor this now. I get x minus 2 equals 0. So x equals 2 is my critical point. So we're going to test what happens on the left and the right side of the critical point. So if I plug in a number, well, let's plug in 0, right? If I plug in 0, I'm going to get a negative 2 and a negative 2. A negative make a positive, times 3 is a positive. Let's plug in, let's say, the number 3. 3 minus 1 is well, any number bigger than 2, it's going to be a positive and a positive. 3 minus 2 is 1. 5 minus 2 is 3. 5 minus 2 is 3. So if I put in a 5, a 3, or whatever, I'm still going to get a positive. So this particle is constantly moving to the right everywhere. We just have a critical point at 2, but this particle is continuously moving to the right. Okay, so always moving right. Okay, my interval, because I'm starting at 0, is 0 to infinity. Okay, and then I want to determine a of t. Well, the derivative of the velocity is a of t. So the derivative of this, I'll do the velocity, or a of t in a different color. Okay, I'm going to take the equation that represents velocity, 3x squared minus 12x plus 12, and I'm going to factor that. And I get a of t equals 6x minus 12. Okay, that is the equation that represents acceleration. Determine the interval on which the velocity of the particle is decreasing. Well, that is going to be when it's concave down, like the picture I had with the bird. Remember, the bird was flying up, and as he's about to change direction, his speed or his velocity is slowing down. So we're going to now set 6x minus 12 equal to 0, and we're going to solve for that. So again, I'm going to factor out a 6. I get x minus 2. Again, I'm going to test it when x equals 2. That's my inflection point. So what's happening to the left of 2? What's happening to the right of 2? Again, I'll plug in 0. 0 minus 2. A negative times a positive is a negative. And then when I get over here to plug in 3, I'm going to get a positive. So we are slowing down. Particle is decreasing when it's concave down or when it's negative, but it's decreasing from 0 to 2. All right, that's that equation. Let's look at another one. Okay, the big lesson in here is that, to get from position to velocity and acceleration, you're going to either take the derivative to get from position to velocity, take the derivative again to get from velocity to acceleration, and then take the integral if you're going in the other direction. So if I were to give you velocity, you can take the integral to get to position, or you can take the derivative to get to acceleration. Let's look at this example here. A particle moves along the x-axis, and its velocity is represented by this equation. Find the function that represents the position. So if I have to remember what order, Zavala, I got this down, SVA. So to find the function that represents position, I have to take this and do the integral, because the integral, my position, S of t, is the integral of v of t. So we're going to put 3t squared minus 16t plus 5, and we're going to now take the integral. So this is going to become t to the third minus 8t squared plus 5t plus c. Okay, and I have to figure out what c is. In this problem, I can't just leave the equation for s of t with a c in it. What I have to do is actually plug in, and notice I've been given some information. The position is 4 when t is 2. So I can plug in 4, and I know that t is 2. So I'm going to go 2 to the third. I'm plugging in t for 2 minus 8 times 2 squared plus 5 times 2 plus c. So now we can solve this equation and find the actual equation. We can figure out what c is and plug it in. So this becomes 4 equals 8 minus 32 plus 10 plus c. So now let's solve this. 8 minus 32 is negative 24 plus 10 plus c. Oh, sorry, that's a 4. Come over here where I have more space. 4 equals negative 14 plus c, or c equals 18. Oh, we solved for c. So now we can plug this in to our equation right here. Here's our equation, s of t. And we know that s of t, the full equation, once we discovered what c is, equals t to the third minus 8t squared plus 5t plus 18. Okay, that's the relationship between position, velocity, and acceleration. Right? I don't know if I have time for another one. I have about a minute left in this video. But if the acceleration is given here, and here at t equals 0, the velocity, it's telling us information. And it's telling us at position. Oh, this is a good one. So here, if I have acceleration, velocity then is I'm going this way. So I'm going to get the integral. So I'm going to get 3t squared minus 18t plus c. I have to plug stuff in. V of 0 is 24. So I'm going to get 24 when I plug in 0. 0 minus 0 plus c. So c equals 24. So we find out that velocity equals 3t squared minus 18t plus 24. And to get to position, we take the integral again. So we're going to get t to the third minus 9t plus 24t plus c. And I'm running out of time on this video, but look at t1, the position is 20. So I'm going to go 20 equals 1 minus 9 plus 24 plus C. Solve for C, and that'd be my answer.